Hi everybody, welcome to lecture 11 of Electrical Engineering 331. And actually this lecture will be divided into three parts, A, B, and C. So this is part 11A. We'll begin by doing something familiar. We'll say, suppose we want to evaluate the convolution of u of t with u of t minus 1. And but once we've done this, then we will do something new and compare it. Okay, so since we're used to having most of our convolutions written in terms of h and x, the first thing I will do is just arbitrarily call one of these functions h of t and the other one I will call x of t. And it doesn't matter which one I choose for h and which one I choose for x. I just want to give them a name. Now, you know that we can write the integral as the integral from negative infinity to infinity of h of tau times x of t minus tau d tau, or as the integral from negative infinity to infinity of h of t minus tau times x of tau d tau. And what I have suggested before is that you choose the form that associates the more complicated argument, that is the t minus tau argument, with the simpler function. So in this case, if we define h to be u of t and x to be u of t minus 1, then I would say that h of t is slightly simpler than x of t, and so I would use the form of the integral h of t minus tau and x of tau. Okay? And so if we do that, then since h of t is u of t, then h of t minus tau will be u of t minus tau. And similarly, since x of t is u of t minus 1, then x of tau will be u of tau minus 1. And as usual, in the convolution integral, we're integrating from negative infinity to infinity. Okay, so now we're going to do this in the usual way first, and then we're going to learn about a new technique. Okay, so using what we've done before, the way that we would evaluate this, one way would be to say, okay, let's get rid of this u of t minus tau term first, by reasoning or by observing that when tau gets bigger than t, this term will disappear. So, and when tau is less than t, this term is just equal to 1. So we can drop out this first term and make the upper limit on the integral t instead of infinity. Now, at this point, we want to evaluate this integral. And what we can observe is that this u of tau minus 1, it turns on, as you're going from left to right, it's equal to 0 until you might say it turns on at tau equals 1, and after tau equals 1, for all values of tau greater than 1, it's equal to 1. So what we then realize is that if this t, which is the upper limit of the integral, if it's less than 1, that means that the integrand never turns on. It's always 0 over this entire range of integration. And so in that case, obviously, the integral would be 0. So if t is less than 1, this integral just gives us 0. But on the other hand, if t is greater than 1, the way we reason is as follows. Okay, as we've just argued, this u of tau minus 1 does not really contribute. The integral is nothing until tau is equal to 1. So we can change in this second case where we assume that t is greater than 1, then we make the lower limit of the integral 1, because that's when we begin to accumulate something. For all values of tau less than 1, we get nothing. So we don't have to go all the way back to negative infinity. We can begin at tau equals 1, and then we stop at tau equals t. And in this range from 1 to t, u of tau minus 1 is just equal to 1. And so that's how we get this second term. And then finally, if we integrate 1 d tau, we get tau evaluated from 1 to t. And so that just gives us this final answer. The convolution is equal to 0 if t is less than 1, and it's equal to t minus 1 if t is greater than 1. And notice, as we expect in this case, at where these two regions join, which is at t equals 1, these two expressions are equal to each other. We would get 0 is equal to 0 at t equals 1. So we have continuity. So that's how we would do the convolution using what we've learned before. But now we want to learn a new method called, your book refers to this as the graphical convolution technique. And let's see how it goes. So we're going to look at 3 different cases just so that you get a feel for how this goes. And the first case will be a repetition of what we just did above using a different method so that we can observe that we do get the same answer, which of course helps to give you a little bit of confidence in the procedure. So again, now we want to evaluate this convolution. But what we're going to do, we have 3 steps in this graphical convolution technique. So let's look at what they are. Okay, what we're going to do in step 1 is look at the function that has the t minus tau argument, which in this case is u of t minus tau. And so we're going to plot part of that function. We're not going to worry about t at first. We'll just plot the u of minus tau as a function of tau. Okay? So u of minus tau looks like this as a function of tau. And that's all you have to do for step 1. Now for step 2, since we're really interested in u of t minus tau rather than u of minus tau, what we want to do is take that graph of u of minus tau and shift it to get u of t minus tau. And we always will begin with the assumption that we're going to vary t, but we're going to assume that t is negative to begin with. So that means we're shifting it to the left. So you can see that we have shifted this curve up here to the left, and the leading edge is at t. Because the leading edge here was at 0, and so when we add t to that, we just get t. Okay. And now the third step, which leads to the final answer, is you draw the graphs of both of your functions, one on top of the other. And notice that I've chosen so that the axes align with each other. And then once I've done that, then I will increase t. I guess I caught that step 4. It doesn't matter if you want to think of that as step 3 or step 4. But anyway, the last part is to increase t as needed to perform the convolution. So here we have u of t minus tau, which we've already done above. I'm just repeating the graph. And here we have the graph of u of tau minus 1. And I've written them one on top of the other so that we can very easily see what the integral is going to be. Now you can easily see that when t is less than 1, these two graphs don't overlap. And so the integral will be 0. So that's what we have right down here. Y of t is equal to 0 if t is less than 1. But notice in this graph here, if we keep increasing t until it gets past 1, then we will have a region of overlap. It will look like this. And we see that between tau equals 1 and tau equals t, we will have this. These two multiplying by each other. We will have overlap. So we have then the integral becomes integral from 1 to t of 1 times 1, which is 1 d tau. And that's true if t is greater than 1. Well, if you integrate 1 d tau, you get tau. And tau evaluated from 1 to t will give you t minus 1. So sure enough, we end up with exactly the same expression doing the convolution using the graphical convolution technique as we did with the technique we had learned previously. So there's our first example, and now let's go to 11b, where we will look at another example that's just slightly more complicated. Okay, so this time we want to convolve u of t with e to the minus t u of t. And so we begin, you might call it step 0 if you wish, by deciding which function we're going to call x of t, which one we're going to call h of t. And as I told you before, it doesn't matter. And then we choose which integral form to use. So I'm going to choose this first function, u of t, to be x, and I'll choose h of t to be the second function, e to the minus t u of t. And then since x is simpler, we'll choose to write the convolution in this form, integral minus infinity to infinity, x of t minus tau, h of tau, d tau. And if you keep in mind that x is equal to u and that h is equal to e to the minus t times u, then we can also write the convolution integral like this. Okay, so now step 1. We're looking at the function that has t minus tau as its argument, and we're going to at first just drop off the t and look at u of minus tau in this case. So u of minus tau looks like this, and then when we shift it by t, we get u of t minus tau looking like this in step 2. And then in step 3, we draw both functions. So e to the minus tau, u of tau is up here. And this function, I think it's clear that's u of t minus tau, but I should write that in. So let me stop for just a moment and correct that. Okay, so now we have that written in there, u of t minus tau. And so we can clearly see that when t is less than 0, as long as t is less than 0, these two graphs don't overlap with each other, so we get 0. But if we keep increasing t until it gets past 0, then we will have overlap between tau equals 0 and tau equals t. And so the integral of the one will just become the integral from 0 to t of e to the minus tau times 1, so we get e to the minus tau times d tau, and that's if t is greater than 0. So we just bring down the 0, and for integral of e to the minus tau d tau, you get minus e to the minus tau, and we're going to evaluate that from 0 to t, and so that will give us minus the quantity e to the minus t minus 1, and so we get then 0 if t is less than 0, and 1 minus e to the minus t if t is greater than 0. And notice again, we can check for continuity at the point where these two regions connect with each other, which is at t equals 0. At t equals 0, this expression is equal to 0, and at t equals 0, this expression is also equal to 0. So they do, there is continuity. And so that's the end of our second example. And now we'll go to our most complicated example in lecture 11. Which will be C. In C, we go ahead from the beginning and we'll just give the name h to this first function and x to the second function. So you see that h is looks like this, and we want to convolve it with x, which looks like this. Now, clearly, the simpler of these two functions would be h, so we will choose to write the convolution in this form, associating the more complicated argument with the simpler function. And so the first thing is to plot this function, but without the t. So we'll have h of negative tau, and so you can see up here if this is h of t, then of course h of tau would be the same thing but with a tau here. So h of negative tau is just that flipped. And then when we shift this by t, where t is initially a negative number, then h of t minus tau looks like this. And now in step 3, we draw both graphs. So here's our graph for x of tau, and here's our graph for h of t minus tau. And you can see that as we increase t, there's not going to be any overlap as long as t is less than 2. So if t is less than 2, the convolution is just equal to 0. I'm calling the convolution y here, because that's usually, I didn't really call it y up here, but of course that's usually what we call the convolution of h and x is y, so that's where that y is coming from. If you wish, instead of having y of t here, you could just call it h of t convolved with x of t. Same thing here, of course, and down here in the answer. If you wish, you could just call that h of t convolved with x of t, if that causes any confusion to you. Okay. But again here, if t is less than 2, there is no overlap, and so the integral is 0. Now, once t gets past 2, we begin to have overlap. But we need to be careful, because we're going to get one expression if t is somewhere between 2 and 4, but then we're going to get another expression once t gets past 4. So we have to look at two different cases, okay? We have to look at the case when t is between 2 and 4, and then also the case when t is greater than 4. Now, if t is over here between 2 and 4, then our region of overlap is between tau equals 2 and tau equals t. So our integral will be between 2 and t, and then when we multiply, this is 1 times 1, so we just get an integrand of 1 d tau. Now, on the other hand, if t keeps on increasing and it's past 4, then the region of overlap will be between 2 and 4. And so we will have integral from 2 to 4 of 1 times 1, which is 1 d tau. And that's what we have if t is greater than 4. So, as usual then, integral of 1 d tau becomes tau. So here we have tau evaluated between 2 and t, and here we have tau evaluated between 2 and 4. And so our final answer down here becomes 0 if t is less than 2, t minus 2 if t is between 2 and 4, and 2 if t is greater than 4. And notice again, we can check for continuity where these regions join. The first two regions join at t equal 2, and at t equal 2, this is equal to 0, and at t equals 2, this is equal to 0. So there's continuity there. And then the second two regions, they touch each other at t equals 4, and at t equals 4, this expression is equal to 4 minus 2, which is 2, and at t equals 4, this expression is equal to 2, so again, we have continuity. And as I said before, this continuity check is it's really just a check to see if you're wrong. Just because it checks out, that doesn't mean that you're correct, but if it doesn't work out, it does mean you've made an error, provided that both of the functions that we're convolving are everywhere finite. Okay, so that is an introduction to the graphical convolution technique, and in your test, you'll see some more examples so you can get some more practice with that. But that concludes lecture 11, and so good luck.